Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, good morning, and it's my pleasure to invite Rafay Hamid to Microsoft to give a talk. Rafay is a researcher at eBay Research Labs. He finished his PhD at Georgia Tech and was an associated researcher at Disney Research in Pittsburgh. Rafay?
Thank you very much, and thanks for having me here and coming to my talk. So, a lot of my work is about automatic video analysis. That is, given a video, how do we figure out what's going on in it? And in today's talk, I'll speak about some of the stuff that I've done in this context over the last few years. So let me start by sharing with you what my opinions are about why should we care about videos and why do videos matter. So video is a unique medium that can capture both the sight and sound of an environment in synchronicity, which makes it really effective to not only capture but also view the everyday human experiences. And it is easy for us today to take video for granted, but at the time when it was invented a little more than 100 years ago, it was nothing short of a miracle. And just to bring that message home, and also for fun, I wanted to share with you this excerpt from a 1950s movie called The Magic Box, where the character of the inventor of the video camera is shown to sort of share his great joy at his remarkable achievement. So let's take a view.
It's a bit like a magic lantern, but instead of one picture at a time, you see 8 or more pictures every second. And that's what you see on that sheet there. 8 pictures every second. And they all merge together into one moving, living picture. See? Of course, there's a bit more to it than that. I'm not saying it's perfect. Far from it. But it works. Can't be praised. It works, doesn't it? You can see that.
So starting with these humble beginnings, video has really become an integral part of our day-to-day life. Today we have millions of users uploading and viewing videos at places like YouTube. We have videos making waves in the social media circle thanks to Vines and Instagram. More and more people are realizing that they can capture information about the products that they want to sell online using video that they cannot by using just text and or images. And being at eBay, this is something that I'm going to talk about a little bit more in detail. The entire model of news reporting is undergoing a complete transformation these days, where any individual with a digital video camera who is at the right place at the right time can capture a breaking event and submit it to one of these news reporting agencies. Also in the field of online education, video is playing a great role, where places like Khan Academy and Udacity are making thorough usage of video to disseminate knowledge to the masses. And last but not least, thanks to the online and on-demand video, the entire model of entertainment has undergone several transformations over the last few years. And so with all these really exciting and interesting things happening with and around digital video, it really feels as if we are living in an era which is at least partly defined by the medium of digital video. So while we've made some commendable progress in terms of capturing and storing and transmitting videos, I still feel that the so-called elusive holy grail remains to be the automatic video analysis. And if we can make some major progress in that direction, then I feel that the opportunities can truly be endless. For example, we could have systems that could be used for automatic healthcare management of senile individuals. With better surveillance systems, we could have improved safety and security. Systems that can understand complicated tasks such as medical surgeries could help us provide useful information, which could therefore help us improve our performance in these complicated tasks. And again, last but not least, we could have automatic sports visualization and analysis systems that could help us engage better with the different types of entertainment and therefore be able to enjoy our lives in a better way. And again, this is something that I'm going to talk about in more detail in just a bit. So to situate my talk better, let me start by showing you an active environment of a soccer field where different players are performing different sports-related activities. So one of the main challenges for automatic video analysis systems is this wide gap that exists between the low-level perceptual data, such as pixel values, and the more interesting high-level semantic stuff. For example, whether a player is kicking a ball or not. And a natural way to bridge this gap is to have a set of intermediate characterizations that could channel this low-level information in an appropriate way such that it could be used at the higher inference level. And one such set of intermediate characterizations start with the assumption that an active environment consists of a set of key objects that define the type of activities that can go on in that environment. So in case of a soccer field, for example, some of these key objects might be the players on the field, the goal post, the ball, and so on. Now, different interactions amongst these key objects over finite durations of time constitute what I call actions. So here, for example, I'm showing you an example instance of the action of kicking. And finally, when we put these actions in a specific temporal order, they constitute what I call activities. So here, for example, I'm showing you an activity which consists of a player throwing the ball to another player, an opposing team player intercepting the pass, and the first player diving at the ball in order to make a save on the goal that is being done by the opposite team. So in this space of activity dynamics, there is a wide range of very difficult and open research challenges that still are there. And in this talk, I wanted to speak about some of the work that I've done at each one of these intermediate characterizations. In particular, for the characterization of key objects, I'll talk about the problem of localizing and tracking these key objects. For the characterization of actions, I'll talk about the problem of spatiotemporal analysis of videos to figure out what are the more important or interesting parts of these videos. And finally, for the characterization of activities, I'll talk about the problem of large-scale activity analysis, particularly using unsupervised or minimally supervised learning methods. So let me start with the characterization of key objects, where the motivating application I want to use for this part of my talk is sports visualization and analysis. So I don't know how many of you remember this match between USA and Algeria in World Cup 2010, but one of the goals that was scored by Team USA was considered an offside foul, and this actually resulted in the US team not winning the match. And so wouldn't it be awesome if we could have visualization systems that could figure out where each one of the players involved in a game is, and then figure out who are the key players that are involved in a particular foul, and then provide us with some visualization information that could help us understand the dynamics of the sports better. And so this is the project that I was involved in at Disney Research Pittsburgh. This was done for ESPN, where the objective is to track these several players, figure out where the second to last defense player is, because that is one of the crucial players to determine whether an offside foul has happened or not, and then draw a virtual offside line, so to speak, underneath that player. And some of the technical challenges that make this problem interesting are tracking under visual occlusions, noisy measurements, and dealing with varying illumination conditions. So I'll start by giving you an overview of the computational framework that we use to solve this problem, and then I will say a few more words about each one of these steps, and along the way, I'll try to identify some of the technical contributions that we made in this project. So starting with the set of input videos, the first step we do is to extract the foreground. And at the end of this step, we have pixels that don't only belong to the players on the field, but also the shadows of these players. And since later on we're going to track these players in the image planes of the cameras, these shadows can become distracting. And therefore, it's important to remove them. And that's exactly what we do in the step of shadow removal. And once we have obtained the blobs of these players, we can actually track them and also classify whether they belong to the offense team or the defense team. And now when we have this sort of spatial information available to us from multiple cameras, we can fuse this information together, search for where the second to last defense player is, and finally draw the virtual offside line underneath that player. So now I'll say a few more words about each one of these steps. So starting with the step of foreground extraction, we begin by building adaptive Gaussian mixture models for each one of the pixels in the scene. And these models are used to classify each pixel whether they belong to the foreground or the background. And this is done by thresholding the appearance likelihood. As you saw previously, after this step of foreground extraction, we get pixels not only from the player's bodies but also the shadows. And since these shadows can be very strong, relying purely on appearance-based methods to remove them don't generally work really well. So for our case, we relied upon some of the 3D constraints of our camera system. And the basic intuition that we are using here is that shadows cast on planar surfaces are actually view invariant. What that means is that if we warp a subset of these views onto a particular view, then the pixels that belong to shadows are only going to be the ones that correspond to each other at the same point. And so by using this very basic invariance and some simple chromatic thresholding, we were able to remove these shadows relatively accurately. With the blobs of the shadow of the players in hand, we can also track them using a particle filter-based tracking mechanism, where the basic intuition is that given the position of a particular player in a particular frame, we use some motion model to hypothesize where this player is going to move in the next frame. And then given the noisy measurement in the next frame, we figure out how good or bad each one of our hypotheses was. And then in maximum likely sense, we can figure out the most likely estimate of where the player is in the next frame. And this process is repeated over the entire length of the input video. So one of the things that went in our benefit for this project was that while classifying these players across different teams.
At what granularity were you doing that? Like predicting where a player is going to be? Is that at a frame level?
It is exactly at a frame level. And I'll talk a little bit more about the data that we captured. And it was either 30 FPS or 60 FPS.
It's strange that you have to rely on a prediction as opposed to just finding what happens in the next frame.
Right. So we could do detection at each frame, but then the problem of how do you ascribe which player corresponds to which player in the next frame is a non-trivial problem. So generally in tracking, they use time information because there's a lot of velocity or first order based information that you can use to simplify the problem. So one of the things that went in our advantage is that the appearance of the players in this problem is by design quite discriminative, because you want the players to wear uniforms from different teams so that you can discriminate the two teams from each other. So for the problem of classifying these blobs, we were able to use simple hue and saturation based cues in a nearest neighbor sense to be able to achieve quite high classification result for this two-class classification problem.
So you're not tracking the goalkeeper?
So we are tracking the goalkeeper, and the goalkeeper had a different template.
Okay.
Yes, that's a good question. So while it was easy for us to classify these players across the team, the flip side of that is that within the team, it's very difficult to detect which measurement belongs to which player, especially when these players come close to each other. And this is really where some of the technical contributions come in. And the way that we tried to solve this problem was to throw redundancy at the problem. So that the idea is that if you track these players in multiple cameras and some of these trackers and some of these cameras fail, you can still rely on other cameras to actually still get to an accurate inference. And to illustrate this point further, here I'm showing you the top-down illustrative figure where several players are shown in one half of the field that are being captured from three partially overlapping cameras. And in an ideal world, if we were only interested in player P4 for now, we would get three different measurements in the image plane from each one of these three cameras, and we could warp these image plane measurements onto a common ground plane, and they would all correspond to the exact same point, and we'll know exactly where this player is. However, real life is not so nice to us, and due to several reasons, we have different types of noises that don't let these three measurements correspond to the exact same point. Now, this becomes a really challenging problem as we have multiple pairs that come very close to each other. And so fundamentally, this becomes a correspondence problem, so that if we could find out what measurements correspond to a particular player, we'd be able to fuse it together and come to an accurate inference. Now, there are several solutions to this problem, and the one that we chose to use was a graph theoretic approach of using a complete k-partite graph, where the number of partites are equal to the number of cameras that we are using. So here I'm showing you a graph with three partites because I'm showing you three cameras. The nodes in each partite corresponds to the observation of where a player is in the 2D position of images. And here I'm showing you for illustrative purposes the color of these nodes to be of the same color as the color of the players that are seen from a particular camera. Now, this is a undirected edge-weighted graph, and the weights on these edges are defined by the Bhattacharya distance between the appearance of any two players. Now, this leaves the notion of how do you figure out what does correspondence in this graph mean. And again, you can have several solutions. For example, you could have the notion of maximum, you could have maximal cliques defining what correspondence means in this graph. However, for our problem, we figured out that using the notion of maximum length cycles was sufficient to have a robust enough result. So the idea is, if we could figure out that these three nodes in the graph form a maximum length cycle, we'd know that these three measurements belong to a particular player. We'd be able to fuse them. And then similarly, if we could find all the cycles in this graph, we'd be able to find out where each one of these players is quite accurately. Now, it turns out that finding these maximum length cycles in k-partite graph is an NP-hard problem for any graph with number of partites greater than or equal to 3. And so we can't really rely on exhaustive search methods to do that, because we needed to do that in pseudo-real time. And so we had to rely on greedy algorithms to do this search, and that presents us with a trade-off between optimality and efficiency. And it turns out that there's a whole class of algorithms that you can use for greedily searching. And one of the contributions of this work was to actually analyze which of these greedy methods work when and how well for our problem.
Can you say a few words about why the inconsistency, where are the inconsistencies come from? Camera calibration, vibration in the ground?
That's a wonderful question. So I'd be more than happy. So camera calibration is definitely one of the reasons, because while we are making the assumption that it is a planar surface, no surface is perfectly planar. So that's one. So there are errors that we get in our homography measurements. Also, because of the sort of lens aberrations of the camera, there are also different types of noise that can be added. So that assumption gets, there's one of the big reasons. The other big reason is the shadow removal step. So just to, actually I should go like this. So just to give you an understanding of that problem, why this really happens, I'll show you a graphic if I can find it. There we go. Okay, so here I'm showing you a scene where I have the shadows of these players that I have marked green, right? And here I'm showing you a picture of a corresponding picture where the shadows have been removed. And while in several of these players the foot pixels are still there, for a lot of them the foot pixels are gone. So essentially, from the system's perspective, they're flying in the air, and so when you project it, they don't correspond to you. So this is one of the big reasons. But yeah, that's a very good question. Right. So just to give you sort of a visual of what this fusion mechanism results in looking like when you actually apply on a real video, this is sort of to give you a sense of how do we fuse different measurements as different players move around in the environment. And this leads us to the point of evaluating this framework. And again, as I mentioned, this work was done for ESPN, and one of the things that they were very keen about was to make sure that whatever statements we make about the accuracy and performance of our system are really backed by a solid number. So to do that, we actually went through quite a bit of work. So I'll present two sets of experiments for this for the evaluation part of it. One of them was done at the Pixar studios in California, where they have a soccer field, and we actually went there and hired a local soccer team. We requested them to play different types of games for us in different types of formations and drills. We also requested them to wear jerseys of different colors, and these colors correspond to the team colors of international teams that take part in World Cup. We also captured this data over several days from 9 a.m. to 6 p.m. to make sure that we were able to incorporate all the different types of illumination conditions that can happen. not only did we test this framework in one setting, but to make sure that our sort of framework is robust over different types of stadiums, we also went down to Florida in Orlando at ESPN Worldwide of Sport, where they have this very large facility where kids from all over the US come to play soccer, amongst other games. So here, as you can see, one of the variables we looked at was whether our system can perform in the conditions of floodlight. Also, you might have noticed that the height of these towers, these cameras, is higher. So in this case, it was 60 feet, whereas in the previous data set, it was 40 feet. Another difference was that here we captured data at 720p, whereas in the previous data set, we captured it at 1080p. And so we wanted to see how does the resolution of the image affect the performance of our framework. And in the interest of time, I'm not going to belabor too many numerical details of our work when compared to baseline. Suffice to say that our overall accuracy gain was close to 10% gain based on some of the baseline methods that we looked at. And if you're interested in finding more about the details, please come talk to me. I'll be happy to talk more about it. So in summary, I just spoke about the problem of fusion as graph theoretic optimization problem, where I treated correspondence as cycles in k-partite graphs. I also spoke about greedy algorithms that can be used for efficient searching of these cycles. And an important point here is that this is a relatively general approach and can be applied to other types of sports, for example, field hockey and basketball and volleyball and so on. And on that note, I wanted to share with you some of the related stuff that I've been involved in that uses this framework. So I am a big squash junkie, and I like to watch a lot of these games on YouTube. So the idea here is that given dozens of videos of matches of a particular player, can we have systems that can understand what are the general trends of that player? What are the different types of techniques that they use against their opponents? So, for example, one of my favorite players is Rami Ashur, who is in the red shirt here. And the question is that if I were to play with Rami Ashur and if I dropped him in the top right corner of the court, is he going to drop me back or is he going to lob me? So these types of questions I know are very important from coaching perspectives. So this type of framework can be used to get us closer to automatically figuring out these trends. And at the risk of jumping the gun a little bit, I understand that I'm not yet talking about this actions detection part of my talk. But since we are talking about sports, I want to say that not only can you look at these sports videos at the macro level, but also you can start looking at it at a relatively less macro level, where each individual action performed by each individual player can start to be classified and recognized, not only when it is being captured from one camera, but also from several cameras together, because that's how usually these activities are captured in sort of World Cup or high-level situations. And finally, so far whatever I've talked about is with static cameras, but more and more people are using handheld mobile devices to capture videos. And so I wanted to say a few words about this thread that I am actually currently involved in at eBay Research. This problem, in fact, relates to the image quality problem. So eBay has a lot of users that they are uploading millions of images online, but they are not very professional photographers. So a lot of the time that they capture images, it has a lot of background clutter. And while we can use techniques like grab cut, etc., to extract these foreground objects from the image, the form factor of a mobile device is such that it does not necessarily always encourage a lot of interaction with the device. And so here the objective was to explore whether we can use the medium of video to extract the foreground objects in a less interactive way. So the idea is very simple, actually. Suppose you want to sell a toy on eBay, and you want to capture it in a certain environment. So you first capture a background video using a handheld camera, and then you put the object in that environment again and take another video with a handheld camera. Now, the question is, with these two videos with very different camera path disparity, can we actually align these videos efficiently so that we can subtract the background video from the foreground video and come up with the output video which only has the foreground object in it? And so, to test our system, and this is still work in the process, to test our system, we actually applied it to different types of scenarios with foreground objects with different types of geometry, complexity, with several foreground objects, multiple foreground objects, different types of illumination conditions, and also different types of movement, articulate movement of the foreground object. And our initial results tell us that this is an interesting way to go towards solving this particular problem.
Back to the soccer project, can you talk about the compute requirements to handle 3 screens of HD, and were you limited by that at all?
That's an excellent question. So to answer that question, let me right. So the compute requirement of the project were that we wanted to show it in pseudo real time, which means that we wanted to show it in terms of instant replay. So we would get about 3 to 4 seconds to process close to 10 seconds of video, and we would need to generate results for that. And so this project was done at a demo level, so it was not at a production level. And the code that was written was by me. It was semi-optimized, not super optimized. And just to give you some understanding of what is the division of the sinks in terms of time. So I was able to bring it to almost 0.4 second per frame. And this is sort of for all 3 frames, so you should divide it by 3 in some sense. So this is cumulative time, and here you can see that most of the time is taken by the background subtraction part of it, which is very, very parallelizable. So I was not using any GPUs to get these numbers. So I think that this number can actually be significantly bring down. But at the point when I got finished with this project, this is sort of the time that we were taking to process video for this. So I was using multi-core, but I was not using multi-core in a very efficient way. I was using OpenMP type of things, but I'm quite certain that we can optimize it to quite a different level.
And what if you had 10, 50 times the compute capability? Would that make your job easier? Would the results be better? Or?
I think that it would help us in 2 ways. One is that it would allow us to try algorithms that are slightly more complex, and therefore it would help us get more accuracy. That's one thing. The other thing is, one of the solutions one of the sort of philosophies of solving this problem was to throw redundancy at the problem. So I'm quite confident, I know for a fact that if you have fewer number of cameras, your accuracy degrades quite steeply. So one thing that having a lot more compute power would give us is to deal with far more number of cameras. So imagine a rig of 50 cameras. Now you can get over the problem of visual occlusion much better. And so that are some of the things that will help us too.
So can you say something about the steps of segmenting the object?
Sure, I'd be happy to. So the way we did segmentation was actually doing sort of a connected component detector. So that's how we started our trackers. And then at each step, we were actually performing background subtraction first. So the notion of segmentation is really at the step of connected components.
First, you need to match between the videos, right? You had 2 handheld videos.
Oh, you're talking about this step. I see. So you are asking me about, yeah, sure, absolutely. I thought we were talking about I see. Yes, I'd be happy to. Okay. Well, I don't know why these videos are not playing right now, but yeah. So the steps are relatively simple. We start with finding the sort of the surf features in the background video, each frame of the background video, and also the surf features in each frame of the foreground video. And then we use for each frame in the foreground video, we actually find the matches, these surf matches, using ransack to figure out what are the best matches here. And then once we have found these matches, now we have a subset of frames that are good matches for that particular frame in the foreground video. And we use sort of projective transform to transform those frames, those background frames that have been matched well. And so
you assume a planar background for this?
Yes, exactly. So this is very similar to sort of a plane plus parallax work that has happened before. And so the idea here is that you actually don't have to build the whole 3D sort of model of the environment.
The first example that you show of the blue doll there, it obviously didn't have a planar background.
Yes, that is absolutely true. It does not have, so the scene doesn't have to be planar, but the idea here is, and I wish that this worked.
That's fine.
But the idea here is that if you actually first do this planar assumption, and then once you have a registered frame, you actually do non-rigid transformation using optical flow on the previously registered frame, then it takes care of some of the sort of depth in the scene that you're not capturing using your assumption. And not just that, you are getting multiple hypotheses. So if you look at
this will fail, for example, if you have something near a corner and you have two planes that goes from near to far?
Two planes that go from near to far?
I'm trying to think of a scenario where it's hard to approximate.
Yes, so So at any situation where two things don't happen, we might fail much more than not. One is if you have a situation where there's a lot of depth in the scene, to the point where the planar assumption that we are making is completely screwing up everything. So that's one situation that we know we fail. The second situation is when for a particular frame in the foreground video, you're not able to come up with a lot of good matches in the background video. And so we know for a fact that in those situations, the algorithm would obviously not be able to work. And so for those types of situations, when we do go into them, we actually rely on tracking. So we are adaptively relying on tracking the pixels that were detected in the previous frame. I see. So right. So I just spent a little bit of time talking about the characterization of key objects with some of the work that I've done in that regard. And now I will speak a bit about the characterization of actions and really looking at this problem from the perspective of figuring out what are the important parts of the video, an interesting part of the video, and the practical application I'll use to motivate this part of my talk is video summarization. So this problem is becoming increasingly important for eBay because sellers are realizing more and more that they want to use the medium of video to capture information about the products that they want to sell online. So if you go to eBay and search for youtube.com, you will be able to find tens of thousands of listings. And what's happening is that these sellers are capturing these videos of the products they want to sell. They're uploading them to YouTube. They're copying the link and embedding them in the description of their listings. And so just to give you a sense of a video that was captured by a seller trying to sell his blue Honda Civic on eBay. Here's that video. And as you can see that the general quality of video is relatively poor. And these videos can go run all the way till 10 minutes. And so with no understanding of which piece of information is, watching a poorly made 10 minutes video can be quite cumbersome. And so the idea behind this project is really to figure out what are the important parts of this video so that you can allow the potential buyer to navigate this video in a more non-linear, less flat manner. Now, a lot of the previous work in video summarization relies upon the content of the video itself. And since the quality of these videos are quite poor, those types of traditional schemes don't work very well. And we know it for sure because we have empirical evidence for that. Now, thankfully, at eBay, we also have millions of images that these sellers are uploading of these products that they want to sell online. So here, for example, I'm showing you some of the still images that the same seller uploaded of the same car. And you can see that these still images are actually of much higher quality compared to a randomly sampled frame from this video. So the question really becomes, how can we use these images as a prior to help us figure out what are some of the more representative parts of the video that these users are generating? So just to give you a very brief overview of our approach. Oh, by the way, I should mention here that this project was done with one of my interns from last year, Aditya Khosla, who is doing his internship this year at the Vision Group. So, and if Aditya is watching, hi to him. So just to give you some overview of the framework that we that we used. We start with the corpus of our unlabeled images, and we use k-means clustering to figure out what are the canonical viewpoints present in our corpus. Not only do we have these individual images, but we also have frames of the videos that these users have uploaded. And incorporating these frames can actually improve the quality of the discovered clusters. So by bootstrapping on the clusters that we found by just using the images, we iteratively incorporate these frames in an EM-type algorithm to iteratively improve the quality of our discovered clusters. And now with these clusters discovered, given a test video, we can ascribe these frames to any one of these discovered clusters and then come up with the final output summary. So a related problem that we explored over the course of this project was how do we do large-scale annotation and evaluation of different summarization algorithms. So a lot of the previous work in this context have heavily relied upon expert knowledge to figure out whether a summarization algorithm is performing well or not. But clearly this view of this solving this problem does not scale very well. So a part of the contribution of this work was to figure out how can we obtain multiple summaries from crowdsourcing such as Amazon Mechanical Turk, AMT, and use each one of these summaries as an instance of ground truth to figure out whether a particular summarization algorithm is performing well or not, and also to compare different summarization algorithms with each other. Now, just like any comparison mechanism, we need some notion of distance between summaries that we are trying to compare to each other. And again, there are several notions of distances that you can use here. And after exploring quite a few of those, we were convinced that using the notion of swift flow as a distance between summaries is actually a good idea. And to just give you a visual sense of how do the search results look like or comparison results look like when we are using swift flow as our distance mechanism. Here I'm showing you in the first column some of the query frames, and on the right I'm showing you some of the retrieved matches that have been sorted in an ascending order. And as you can see, that swift flow is actually quite robust to the types of variations in illumination and viewpoint that we actually observe in our data.
So the right column is a match to the left column. What's the relation between the speedometer and the car?
Right. So first of all, for each one of these rows is independent from other row. And here, these guys are the closest matches, and this is the farthest matches. And as you can see that here the speedo is very, very similar, and here it is sort of similar, and there it is not similar. So with this notion of distance in place, our problem really sort of boils down to the question of correspondence. We need to find the correspondence between the frames, summarization frames that an algorithm gives us and the summarization frame that an AMT summary has given us. And for that, we can actually use the model of a bipartite graph, where the weights on these bipartite graphs are found using the swift flow as a distance. And now we can use the sort of classic notions of precision and recall to actually figure out how well or poorly is an algorithm performing, and also to compare different algorithms with each other.
So what was the measurement on the Amazon Mechanical Turk? What did you look at? What people do?
Right. So basically what we asked them to do was we gave them a video and we asked them to come up with a sort of set of, we basically showed them a video and we asked them to come up with a set of frames from that video that they feel are the most representative of that video. So for each one of the videos, I'm going to talk about the particular test data in a bit, but for each of the video that we used, we asked several AMTs, Turkers, and we filtered a whole bunch of them out, kept only the top 10 Turkers, and we use each one of these as an instance of ground truth to figure out whether a particular algorithm is performing good or not.
Okay. Because I would argue that, and you get an awesome example there with the car, where I want to sell the car. I set the set of nice photos that will do a good job sell of the car, and then actually for me as a buyer in the video, what was interesting was not what the main pictures showed, but maybe the scratches on the back, which were not in the images.
Right. So that is an excellent question, and that is a very fair point. And the idea here is that while those types of so we would only be able to do that at the moment in our algorithm if we have that type of information available in our image corpus. So if some people have shown scratches and have taken pictures of their scratches as individual images, then only we would be able to do that. And so we are right now relying very heavily on the content of the image corpus. You're absolutely right. And one of the things that we are looking at going forward is how do we add additional information that is not present in the image corpus. So that's a completely valid point. So to say a few words about the data set that we actually used to explore this problem, we focused on the verticals of cars and trucks on eBay because this is the most popular category of products that people use videos to describe their products. We used 500,000 vehicle images as positive example, and also we used the Pascal 2007 data set as the negative examples. We downloaded 180 videos from YouTube of eBay sellers, and we used 25 of these as training and 155 of them as testing. Again, in the interest of time, I won't be able to go over too many numerical details of the results that we captured, but suffice to say that our performance gains were greater than 10% over the benchmarks that we actually looked at, which were several. And we also did some quantitative and qualitative, both types of analyses. And if you're interested in knowing more about the details of the numbers, please talk to me after the talk, and I'll be happy to chat with you.
So regardless of numbers, just as the task is, say, take a video of maximum length for 10% of the original video that corresponds to the original pictures associated with that car.
Right. So the way that we are doing the evaluation is in terms of average precision, and the way it works is so you have a particular video. And you have a particular summarization result from a particular tracker, and now you compare it to the results that were given to us by a particular summarization algorithm, and that would give you one instance of the average precision, and now you average it over the entire set of trackers that you have, and so that's one value, and then you average it over the entire set of 155 testing video that we used. So, and then we compare it using different types of summarization algorithms like uniform, random, k-mean, spectral, and so on. So in summary, I spoke about using web images as prior to perform large-scale summarization of user-generated videos. I spoke about also the use of crowdsourcing for large-scale evaluation of these summarization algorithms. And again, we like to believe that this is a relatively more general approach. And so one of the things that we are currently trying to look into is whether we can use these types of approaches to summarize more wider variety of videos, user-generated videos online, such as birthday parties and weddings. So any video, any class of videos where you have image corpus that actually captures the geometry and general appearance of the scene can be thought of as being looked at using our method. Right. So I just spoke about the characterization of actions, particularly looking at figuring out what are the important parts of the video that are interesting or important. And now I'd like to spend a few minutes talking about the characterization of activities, specifically focusing on the problem of large-scale activity analysis. And the practical problem that I want to use to motivate this part of my talk is automatic video surveillance. So just to give you the big picture of this part of the talk, this was some of the work that I did for my PhD. And in the context of activity analysis at that time and also today, one of the main assumptions that people make is that the structure of the activity that the system is supposed to detect is known a priori. So for example, imagine you're making a dish in the kitchen, and we want to make a system that can recognize whether you're making that dish in the kitchen or whether you're making the dish correctly in the kitchen. We have to make an assumption that the system knows the structure in which that dish is made. So for example, if you're making an omelette, we would need to know that first you're supposed to open the fridge, take some eggs out, heat up the pan, and so on and so forth. Now, this assumption works perfectly well if the number of categories that you're looking into is relatively small. But it doesn't really scale well when you have several categories. In fact, when you don't even know the number of categories a priori, right? So that was the focus of this particular work, that we want to be able to figure out the main behaviors, the main types of behaviors in an environment in an unsupervised or minimally supervised manner. And so this was done over a course of 5-6 years. And in retrospect, if I look back and I were to sort of concisely describe the main findings of the work, I would say that it is that we should look at activities as finite sequences of discrete actions. And so as soon as you start looking at activities like that, you realize that it is very similar to how researchers in natural language processing have looked at documents, because they look at documents as finite sequences of discrete words. And once you do that, once you make that connection, you're able to steal away a lot of the representations and algorithms that these folks have been doing over several years. So I was the one to identify this and therefore build the bridge between these two sort of research communities. And the main idea here is to be able to learn about these activities without knowing the structure, and only by using the statistics of the local structure. So on that note, I'll say a few words about the general sort of the framework that we use. So starting with the corpus of K activities, we use some representation to extract some sequential features of these activity sequences. And we can define some notion of distance based on these event subsequences, using which we can find the different types of classes that are existing in that environment. And once we have discovered these classes, we can perform the task of classification of a new activity and also figuring out whether something anomalous or irregular is happening in that activity instance. So while I explored several different sequential representations for my PhD, here I will only briefly mention the representation of event n-grams, where an n-gram is a contiguous subsequence of events. So the idea here is that you go find these contiguous subsequences, and then based on the counts of these subsequences, you figure out what's going on. So just to show you some of the experiments that we did using the notion of event n-grams to figure out how good or bad this representation is, we actually captured some delivery data in one of the loading docks of a bookstore right next to Georgia Tech. So this is a Barnes & Noble's bookstore. And please don't ask me how we managed to convince the manager of the bookstore to capture data over long durations of time. But in any case, we sort of placed 2 overlapping cameras to capture some of the vantage points of the loading dock area. We captured activities daily from 9 a.m. to 5 p.m. For 5 days a week over a month. And we were able to capture 195 activity sequences. And just for fun, I should mention that this was done at the end of the year. And so by the end of this project, I was really sick of listening to Christmas songs, and I couldn't bear to hear one more Christmas song.
You have audio input too.
Well, for me, yes, we did. So using these 195 activities, we randomly selected 150 as training activities.
What is an activity?
Yes, so that's a great question. So here an activity is defined as the time when a loading sort of a vehicle, a delivery vehicle, enters the loading dock, and the time when it leaves the loading dock. Yeah. So for these types of situations, and also kitchen type of situations, the start and end of figuring out where the start and end of an activity is relatively easy. But there are several situations where finding the start and end or segmenting activity from a stream of events is non-trivial. And so I've done some work which I'll be happy to talk about later if you're interested. But that's an open problem. It's a non-trivial question. So we randomly picked 150 training activities and 45 testing activities. And in this environment, there were 10 key objects. So an example of a key object is the back door of a delivery vehicle. And also the size of the action vocabulary here was 61. So for example, an example of an action in this environment would be a person opens the back door of a delivery vehicle. So using these 150 training examples, here I'm showing you the adjacency matrix of the unclustered instances of these training examples. And here I'm showing you the same adjacency matrix reordered according to the clusters that we discovered in the data.
What's the features?
Right, so the features are, as I mentioned, so this is using event n-grams as a representation, and the features are really the counts of these n-grams. So So this defines an n-gram in an activity. And the features are really the sort of the counts of which n-gram happened how many times. And so based on the difference in these n-grams, you can determine the distance between any two instances of activities.
And how did you find those n-grams?
Right. So the way that we find these n-grams is just parsing over the entire activity. So you know the start of the activity, you know the end of the activity, you know which actions happen. You go and find the first n-gram, you count it as 1. If you find it another instance, you add count before.
So for those 140, 50 training, someone has manually go out and...
No, that's not true. So for this problem, since the high-level inference that we are making is quite high, the thing that was provided to the system was only the sort of sparse tracks of the location of where these key objects are. And so based on that, we actually build action detectors that in fact detected these actions automatically. So the part of tracking was not done for this project, but everything above that was done. So all the results that I'm showing you have all types of errors that were incorporated using automatic steps for each one of these individual steps. Right. So we were able to discover 7 cohesive classes in our data. And just to give you some semantic notion of what a class implies in this environment, so the most cohesive class that we were able to find consisted of all activities that were from UPS delivery vehicles. And there was no explicit knowledge about the fact that it is a UPS truck in our event vocabulary. So the fact that we were able to find all the deliveries automatically that was of a particular type of delivery vehicle makes us believe that the lower level perceptual bias that we are adding to our system is being successfully lashed onto at the higher level. And there were several activities that did not get clustered into any one of the discovered classes because they were so different from any of the other activities. And we treat them as irregularities or anomalies. So just to give you some example of the detected anomalies that we were able to find was, in the first case, we are showing you the anomaly where the back door of the delivery vehicle was left open, which can actually be very dangerous. In the second one, I'm showing you an activity where more than usual number of people were involved in the delivery activity. And lastly, I'm showing you an example of an anomaly where a janitor is shown cleaning the floor of the go down, which is actually a very unusual thing to do. Which brings us to an important point about the fact that while I'm calling them anomalies, this is a misnomer. They are not really anomalies. These are just unusual occurrences. And so the idea in which this type of a system could possibly be used is to just filter out the activities that are relatively suspicious, and then the human should be brought in the loop who should make the decision whether these are just irregularities or actual anomalies. So in conclusion, basically I started my talk identifying this large gap that exists between the low-level perceptual data and the more interesting higher-level inference stage. And I basically made a case for using these key objects, actions, and activities as intermediate characterizations to channel this information from the low level all the way to the high level. And my hope is that over the course of the talk, I was able to somewhat convince you that using these set of these characterizations is at least a useful way to sort of channel this information, particularly from the perspective of some of the problems that I talked about. I should also mention that this is a very open problem. How do you bridge this gap? This is one of the big problems out there. And I'm not at all suggesting that this is the right way to bridge this gap. And in fact, much more research needs to be done before we can actually get to that question. And I've also had the chance of working on several other industrial projects over the last 10 years or so. And so I wanted to say a few words about them. And if you're interested in talking to me about it afterwards, please do. So one of the first projects that I was involved in at eBay was this app called eBay Fashion App. And we built this project called eBay Image Swatch as a feature in this app. And the idea here is content-based image retrieval. So suppose I like your jacket, I take a picture of your jacket, and I want to see if eBay has this type of jacket in its inventory or not in really, really quick amounts of time. So this project was done by a team of 3 individuals, and I was one of the 3 people. And all the way from ideation to productization, we did it all ourselves. In fact, if you download the app right now, the code that is written is partly by me, which is running on the server. So this was a lot of fun, got some traction both inside and outside eBay. It was featured on several news channels. And
kind of feature are used for retrieval?
Yeah, so that's a great question, and unfortunately I cannot talk about it.
No, there's a paper on that.
Yes, so please read the paper. So the types of features that we are sort of sharing with other people are...
I see. I'll look at the paper.
Okay, sounds good. So another project that I want to mention here is that I did one of my internships at Microsoft Research back in 2007, where I had the privilege of working on this project called Microsoft RingCam, where the research problem is really audio-visual speaker detection. And while my work on this project was only over 3 months of time, it really gave me the perspective of how to do research when you're working for a project that is driven towards a product. And also I wanted to say a few words about the project that I did for General Motors before actually starting my PhD career. So here the problem is that we want to detect whether in case of an accident we want to deploy the airbag or not. And the motivation here is that a lot of the times in US, for a non-trivial percentage of time, the fatality of the passenger actually happens because of the impact from the airbag and not the accident itself. So the idea here is that we need to determine in real time whether we should deploy the airbag in case of an accident or not. And so I wanted to say a few words about some of the future themes that I am interested in. The big message here is that I am particularly driven by problems that have a particular goal in mind. And so that is something that I've done in the past and hope to do in the future as well. But as far as some of the thoughts about some future research themes are concerned, over the last couple of years at eBay, I have had the privilege of working with some folks from large-scale machine learning, large-scale data analysis side of the spectrum. And I was lucky to learn some of the stuff from these people. And I am very interested in bringing that knowledge back to the video analysis side of the spectrum and to figure out how can we use those types of representations and learning mechanisms to do inference for problems in video. Because in my opinion, video is one of the biggest sources of big data out there, and we really need to bridge this gap between these two communities. Another thing that I'm super excited about is this notion of mobile media computing. I really strongly feel that this is definitely going to change the way that we understand computing. However, I feel that right now there are really 2 threads that people are really focusing very heavily on. One of them is the capture side of the spectrum, and the other is the compute side of the spectrum. And in capture side, every year better and better cell phones come in, which are able to let you capture the experiences in a smarter, faster way. However, we don't know which types of information are we supposed to sort of extract from these capturing devices, because there's a wide gap that exists between the capture and the compute sense. It's not clear which piece of information should you communicate to the compute side of the spectrum. And I really think that figuring out what are the important and interesting parts of the information so that you only then communicate that part is opening up really interesting sets of challenges. And last but not least, I'm actually very interested in applying vision for robotics, and especially in terms of human-robot interaction. So a lot of my work in the past is about detecting and analyzing activities and actions of humans. And for the field of human-robot interaction, it's really important for a robot to understand what the state of the human is and what the likely next state of the human is. So I think that from that perspective, I can bring in some value on the table when it comes to bridging the gap between the field of computer vision and also human-robot interaction. At the end, I'd like to say a few words to thank a lot of the people who helped me do all this work that I presented today. At eBay Research, I collaborate closely with Dennis DeCoste. I had the pleasure of working with CJ Lin and Atish Sharma. At Disney Research, my postdoc manager was Professor Jessica Hodgins. My PhD advisor was Aaron Bobick. Also, I had a great time interning at several industrial research places, especially Cha Zhang was my mentor at MSR, and Also, I had the privilege of mentoring quite a few wonderful interns and mentees, and they really helped me do a lot of the stuff that I have presented today. So thank you very much, and at this point, I'll take more questions from you guys.
Thank you. Anyone has questions? We asked you so many questions during the talk.
Did you get a chance to work with depth information, RGB plus depth video sequences?
Not much right so far. No, I have not had too much chance to work with RGB data yet. But I'm very interested in sort of working with that, figuring out how to use it.
Okay.
Seems like it would help a lot for the soccer.
Right.
Yeah, if you can get depth at that level, yeah.
For squash is very
I'm thinking for squash.
structured domain, so you have the field that can help you. I have another question. You work with videos on big data, and one of the major problems I saw with videos is how to dig the data out of. It's not as, I wouldn't say photos are well organized, but at least they have tags and they have sometimes GPS locations and videos are horrible. Just try to find all the videos that maybe tourists took in Venice, and you'll get the amount of noise that you get in retrieval there is
Incredible.
enormous.
Yeah.
So, any thoughts about that?
Yes, several thoughts about that. So, first thought is absolutely I agree with you. It's a very, very difficult question. I think that there are several ways to look at this, and it really depends on the context. So, I think that if you are looking at very specific context where the environment is known, then some sort of structured information can be added. But in general, from a generic perspective, I actually very strongly believe in using these images that have tags and geo and textual information available as a prior to actually figure out which part of the video do they belong to, and if they belong to quite a large part of the video, then using that information to classify what is the content of the video. So I think the particular direction that I am very interested in for the specific problem that you mentioned is to rely upon the image information that we have out there. We have quite good quality image information, much better than the user-generated video, and we also have very good amount of textual information, geo information available with these images. So the direction in which I would like to explore it is to how to use that information for this problem. And I think that our summarization work is sort of a baby step towards that. And I hinted at using that type of an approach for other types of problems as well, like figuring out wedding videos, figuring out birthday parties, which are really event related. So we are really going from very simple product video to a more complex event video. So I think that would be some of my thoughts how to look at that.
Okay. Thanks.
Thank you.
Thank you very much.